All right, in the last lesson, we ended up with our analysis of vector fields and the vector and the scalar potential. And in this lesson, we're going to do the same thing, but we're going to extract it right out of Landau and Lifshitz, which is a very difficult book, but we're going to go page 44, section 16 in almost every modern version of the text. And we're going to see how they get to the same spot in a much more direct way, but a way that requires a little bit more mathematical intuition about their notation, and their whole method is a little bit more, well, I guess it's non-intuitive, although none of this is particularly intuitive. The point is that Landau and Lifshitz start with the action alone, right? This is the action. You will not be seeing in this initial part the Lagrangian, right? We're going to get to a Lagrangian, but they start straight up with the action, and they're going to choose. Their goal is to choose a relativistically invariant action, and we already know that for a free particle, its relativistic invariant action is minus mc ds, where ds is an infinitesimal piece of the world line of the particle, and it's integrated from the start of that world line to the finish of that world line. And what they're going to say is, okay, we've already got that for the free particle. What's the simplest possible potential we could add to the Lagrangian that's Lorentz invariant? And then they say, well, there's some vector out there, which we're going to call A, and it has components AI, and we're going to express them as the covariant components right here. And that is Lorentz invariant. It's because it's a 4-vector. So this is a 4-vector A, a 4-vector, not a 3-vector like the A we had before. It's a 4-vector. And to turn it into a scalar, we're going to contract it component by component along the path of the particle. And we're going to integrate from the start of the path to the finish. So right away, the only assumption they have is this is the simplest possible Lorentz invariant thing that they could think of, was this vector field A, and in order to make it a scalar, the most simple thing they could think of is, again, to integrate it along the path. Now, right away you see this kind of mathematical puzzlement that here the path is represented as ds, and here it's represented as dxi. So what they want you to understand is that ds is literally defined as this Einstein sum of these infinitesimal component-wise motions along the path, square rooted, because this is a number, right? This is a little chunk of displacement. This is a little chunk of displacement. You're summing them together. That's a tiny number. You can take the square root of a tiny number. So it is literally calculated like this. So ds is understood to be this. And we need to understand that really well for this to make sense. First of all, this here can be blown up into an integral of each component, a0 dx0, a1 dx1, a2 dx2, a3 dx3. Each of these from the start to the finish of the path, right? So that's literally what this green stuff is literally what this integrated here means, right? So now let's see if we can get a good sense of what the connection is between ds and dxi. All right, so let's just sort of sketch it out. We'll create a space-time diagram where we have time on this axis and space is on this axis. And we will throw down the path of our particle through space-time, which will be this blue line. Now that path is given by 4 functions: x0 of a parameter sigma, x1 of a parameter sigma, x2 of a parameter sigma, and x3 of a parameter sigma, right? So sigma parameterizes where you are on this path. So you might say sigma equals 0 here, and you might say sigma equals 1 there, and this could be the start, and this could be the end of the integral, right? And we know the exact position of the particle in space-time if we know these 4 functions. And in fact, that's one of the goals of general relativity, special relativity, to be able to sort of calculate the path of things through space-time. So you want to know what these four functions are. And usually sigma is given by the proper time tau, usually. But especially in special relativity, right? We parameterize the path along with the proper time. And in general relativity too, in general relativity, you're looking for geodesic paths in space-time, and they're almost always most logically parameterized, at least in the elementary work, by the proper time. So the point is that we can talk about this path in a very small range, right? We can talk about the length of that little piece of path, and that length of that little piece of path is ds. And that little piece of path's length is clearly going to be, if we blow it up even more, it'll be a little bit of dx1. It'll be a little bit of dx2, and it'll be a little bit of dx3, and it'll be, to close it up, it'll be some dx0. And each of these is also, when I write dx1, what I'm really writing is dx1 of the parameter sigma, right? So there's always that inferred parameter there. And so the point is that an integral, if I take an integral over ds and an integral over dxi, I'm really talking about the same path, right? I'm just expressing that path in two different ways. And that's the key I'm trying to show here, is that these two integrals in our work, here and here, the way I've written it, it's one integral with two different differentials. I want to make it very clear. It's one integral along the same path. The path is just expressed as ds, and here the path is expressed as dxi. And then this part of the integral actually blows up into four component parts. But we're not going to do those four component parts right away. But it is important for understanding. But we have one path and two different expressions. And the expressions are literally connected by this, mathematically speaking, and we will use that. But it's important to understand we're dealing with a path and these different expressions for the path. But ultimately, these four functions are really the brass tacks of the whole process. So what do? Well, we have this vector field I. Now notice this time I've got E over C. And before I bragged, in the last lesson, I bragged about how I don't like to throw units in the beginning. So this time I'm going to, first of all, because literally Landau and Lifshitz does this too, right? But also, we do know where the answer is in this case, right? We've just worked through the problem. So there's no point in calling this, C with some proportionality constant, or just C without a proportionality constant, and then later pulling out constants. So we're just going to start with E over C to begin with. But understand, you could just call this A, and you could just leave these out, get to the end, and then start playing around with units and deciding what units you want to study and pull units out. But we're going to just do that from the beginning in this case. So what do we put in for A? Well, A is a 4-vector, right? So all 4 vectors in there, this is now the contravariant form. Notice this is the contravariant form of the 4-vector. It has a time component and a space component. So we're just going to write out the time component as phi and the space component as a vector. Now notice this is still a vector field, right? It's absolutely critical to understand that AI is a function of, well, I guess what I'm just calling it is x mu now, right? It's a function of on space-time, right? Where we have x0 is a stand-in for time, and x1 is a stand-in, well, x0 is time, x1 is the first space component, second space component is x2, and x3 is the third space component, right? So this is a function of space-time, and that gets delivered directly into the vector and scalar parts. Now the vector part of this 4-vector is just the space part. It's a way I'm calling the space part. That is, this is the space part, and we're going to conveniently write it as a 3 vector, and this is the time part, which we're going to conveniently write as a scalar. And we know from our study of special relativity that the covariant expression for this just drops a minus sign on the space part, given the convention that we're using, which is that the metric is going to be 1 minus 1 minus 1 minus 1. When I equals j, these are the values you get for the metric, right? That's sort of elementary special relativity. I don't feel the need to review that, but this is the covariant part, which is what we're using here. So now, what's the next step? Well, now we look kind of, now we're going to kind of make this integral. We're going to deal with this fact that we have these two different differentials here, and we're going to look at ds, and we're going to say, oh, well, that's just the speed of light times the proper time, and that converts the proper time to a distance. And that's just the speed of light over gamma times the laboratory time. So we're going to quickly make that substitution, and now we have a dt. This a, so that takes care of this guy. This guy ends up, hold on, where does it end up? Oh, yeah, this guy here, all of this, flows through this idea and lands right here, mc squared over gamma dt, right? Because you pick up, you've got an mc in our free particle Lagrangian, and then you pick up another c here when you convert ds to laboratory time, and then gamma is a function of the velocity of the particle, and that lands up as a functional, that lands up as an argument of gamma, right? So gamma is a function of the velocity of the particle. So that is how the first piece is taken care of. And then we look at this part, right? So this part gets broken up just like I've described over here. Gets broken up into a space part and a time part. And that's not very difficult to do. You take the vector part and you dot it into the vector part of the differential. You turn dxi essentially. That's a good point. I should write that down. dxi is going to be expressed as dt dr, right, like this. And so when you do that, this piece breaks up into the space part and the time part. And here's where we start seeing the c, this 1 over c help out, because the time part, right, remember the time part here is going to be dx0, but that is just equal to c dt, right? So now to get this dt here, we've taken dx0, converted it to c dt, and now these c's will cancel, and you'll just end up with e phi dt. So that is how that works. So that takes us from so the time part flows through all of this to here, and the space part flows through this dr, and and then we look at, well, how do we get rid of this dr? Well, dr will become dr dt dt, right? And dr dt is just the regular velocity, right? So it becomes the velocity times the time. So this dr flows through this and lands, a dot dr becomes a dot v dt, right? And that's how we get rid of the dr. Actually, let me clean that up a bit. Here's the way we get rid of dr. dr becomes dr dt dt, which is the regular velocity, right? The regular velocity v dt. And then that replacement, this dot product turns into this dot product. All the vectors stuff is in dr dt. So it's a dot v dt. It is the way this flows into this expression. And so now, the reason we've done all this is now we have one integral with the same differential on each term, and we can pull that differential out, and now we have something that looks like a Lagrangian. And this is indeed the Lagrangian of a free particle that we studied a couple lessons ago. And this is the implications of just choosing a very simple, the simplest possible, vector Lagrangian that is Lorentz invariant, or the simplest possible Lorentz invariant Lagrangian that I can think of. And we just threw it in there to see what would happen. And what happens is it breaks up into the space part and gives you a scalar or a vector piece to the potential, right? And it breaks up into a scalar part that gives you this scalar piece of the potential. And you turn the vector piece of the potential into a scalar by dotting it into the velocity. So it's velocity dependent. So the vector part ends up being velocity dependent, and the scalar part is well, it's just the scalar part. You don't have to do anything to that. It's not velocity dependent. And by my judicious choice of units, it's proportional to the electric field, right? And so I'm going to call that the Lagrangian, right? The Lagrangian is whatever is in the action that is integrated against time, and that's exactly what this piece is. So when we land here, this was just done on the assumption of Lorentz invariance, right? You know, this vector Lorentz invariant piece, which was a vector, broke into the two parts that lands up with something proportional to velocity or proportional to charge, and well, I guess what is it? Proportional to charge and linear in velocity, right? And so here you have the comparison from our last lesson, which is where we started. Whoops. See, this is me screwing up those gammas again, right? There, that's better. So now this is what we guessed based on our on the Lorentz force law, and this is what we ended up with based on just Lorentz invariance. And you'll notice it's the same. So we can now proceed exactly like we did in the last lesson from here, right? Because this piece is related to this piece, and this piece is related to that piece. So all the logic from the last lesson applies, except at the end we're not going to have to make any tricky substitutions, right? So so you can decide which is better, right? I mean, Landau and Lifshitz clearly lean on the principle of least action purely and the notion of Lorentz invariance. This part here, this analysis is all based on Lorentz invariance, but once you get to here, now you're going to use Euler's law and the principle of least action. Well, you're going to use the principle of least action to use Euler's law to take, the appropriate derivatives of this Lagrangian and come up to the same conclusions. The difference is that in the end, you won't put the Lorentz force law over here when you do it this way. What you'll do is you'll flush this whole thing out and you'll say Lorentz invariance implies that you should have a Lorentz force law. This implies that there is a force which equals E, that's proportional to E plus V over C cross B, right, with the appropriate definitions for E and B. And in those appropriate definitions will end up looking like del cross A for B. It'll be, they'll end up making a substitution just to simplify things, and they'll call that the B field. And they'll make a substitution for E to simplify things, and they'll call that the electric field, right? Minus del phi. And then they'll say, well, let's go do some experiments to see if that's how forces act in the real world, right? And then they'll discover they do, and they'll say, oh, okay, so I guess there is a potential out there that can capture these electric and magnetic field forces. I suppose that's what would happen. the point is then, or you could get to this spot and say, hey, you could get to the end of this analysis and then say, oh, you know what? I know from experiment that there is this Lorentz force out there, and Maxwell's equations are correct, and et cetera, et cetera. The point is you have two different ways of making an assumption about the this piece of the Lagrangian. Instead of K, I should write L free, right? But there's two different ways. You do the Lorentz force assumptions, or you do Lorentz invariance. And Landau and Lifshitz like Lorentz invariance. Okay, so now let's look at the next thing, which is the derivation of the electromagnetic field tensor from all of this. So now we are going to proceed with Landau and Lifshitz, the same classical theory of fields, but this time page 60, section 23. I just love this this flow. It's not something I've typically seen in most other books, although I think Jackson actually does something a bit similar to this, so I shouldn't be too quick to say that. But this is difficult, but it's not impossible, and it certainly is a great way of exploring all of this mathematics. What we're going to do now is we're going to start. Our goal is to derive something that looks like the electromagnetic field tensor, because that's an important part of field theory. It's so foundational that you really have to know where it comes from and why it was proposed, or why it's a thing. And this is just one way of understanding that. What we're going to do is we're going to write down the action for a particle moving in an electromagnetic field, which we've now decided is this thing. This is the action. Right? We've got our little ds, our little dxi, just like before. We're writing down the same action. Now we're not trying to discover the equations of motion necessarily. We're now going to just discover what is implied by just taking a direct variation of the action. Right? This is how we derived the Euler-Lagrange equations. But now we're going to explore the variation of this action literally, right? Straight from scratch. So what does it mean, first of all, to vary the action? Well, we're going to be using this shorthand notation of this Greek letter lowercase delta, and that's going to be understood as the variation. And d is going to be a differential. So I should be using the language, a differential of a function, the variation of a function. So s is a function, right? The action is a function. So we're taking the variation of an action. So I'm going to take the variation of, and this is the definition of this action. So now, understanding how this variation works, it's a bit tricky. I did a whole lesson on it earlier, but the short version, the too long didn't read version, the TLDR version, is that you can treat this exactly like you would treat a differential, with one caveat. You cannot integrate over the variation of some function. You can integrate over the differential of a function, or a differential of a variable, but you cannot integrate over the variation. So that's really the only difference. Otherwise, you can pretty much treat it exactly the same way. So with that in mind, we're going to take the variation of this integral. So this is a differential for this purpose, so we will linearly move it in and take the variation of this term and the variation of this term. So the question is now, what do we literally mean by variation? And how do we understand the variation of each of these terms? So let's take a brief pause to study just that point. So let's begin by drawing a path of a particle through space-time. Right? And this path, we've already pointed out, is given as a function of a parameter sigma. The reason it's a one-dimensional path is you only end up with one parameter sigma here. And the coordinates of any point along this path are given by these four functions. And so just for simplicity, we'll say that the beginning of the path, sigma equals 0, and the end of the path, sigma equals 1, right? I guess I could call these guys like the path functions or something similar to that. I'll just call it the path. When I refer to the path, you should be thinking these four functions, right? That's what the path is. Then the path has differentials, right? There is, you can imagine easily taking the differential of a path. You can take dx0, you can take dx1, dx2, and dx3, and that would be this little pieces of the components. So this is the differentials of the components of the path. So these are the differentials of the path components, right? So now we need to talk about a variation of the path. So we start at the same spot and we end at the same spot. That's the only restriction the variation has, and the variation is just basically some other path, right? And the idea is that this path isn't very far away from the original path. And whenever we talk about being far away, we're almost always saying that something is so small that when you square it, you ignore it, right? That's what far away kind of means in this business. But here, let's call this red line. Actually, I'll stick to a more classical drawing here. Let's say this is the varied path, right? It looks like that. So now this is the varied path. I guess I could call it that. But what I really want is some language to explain that when I have a value of sigma, right, and this position is x mu of sigma, I want to know the varied path, which would be red, right? The varied path also has a value at the same value of sigma. I want to know the difference in position between those two paths at a value sigma, right? And so that is the variation, with the TION of the path. And what I'm basically doing is I'm taking the components of the path and I'm adding the variation to get the components of the varied path. And that's what I mean by delta x mu of sigma. Delta x mu of sigma means that the varied path, which I will write as x mu of sigma in red, equals delta x mu of sigma plus x mu of sigma, right? So this is these are the guys that connect the components of the true path with the varied path. Now, the only way I'm writing varied path, the only distinction is I'm using the color to distinguish the varied path from the true path. But probably you'll never see that in a textbook, of course. So I probably should write, the varied path as, say, y, right? Y of mu. But the point is this is the path variation, right, at a point sigma, and this is the true path, and this is the varied path, right? So now I might be interested in the differential of the varied path, right? And if I wanted to know the differential of the varied path, I would write dy mu, I'll drop the sigmas now, is equal to d, the differential of the variation, well, I'm dropping the sigma, sorry, the variation plus the true path, right? But the differential of the variation, but the differential is linear, so I get the differential of the variation plus the differential of the true path. Now, this part we understand, right? This part is these little differentials of the path components. This part looks really weird, right? This is the differential of a variation of the path, right? But remember, the variation of a path, that's just a small number that is a function, right? It is the variation of x as a function of this parameter sigma. So this is just a function. So you can take the differential of a function, right? So Landau and Lifshitz uses this symbol here, and it's kind of confusing, but that's what it means, right? And the only other thing we have to remember, of course, is we definitely have to remember that the variation of the path at 0 equals the variation of the path at 1 which equals 0, right? That's to capture the fact that the path begins and ends. The very path begins and ends at the same spot. All right, so that is an important, the intent of this is for you to see that this differential of a variation is a logical thing, because you have to understand these guys are functions just like anything else. They're just very small numbers in principle. So if you ever took this and squared it, we would ignore it, right? Okay, so now back to the main line of development. So the way we're going to do this is we're going to take the variation of the action, variation of this integral, variation of the first term. Let's look at the variation of the first term. Well, we know that ds squared equals this expression by definition, right? That's the definition of what ds squared is. So now what we want is this is a constant, mc is a constant. So we want the variation of ds, which is the variation of the square root of this expression. So here we're actually using this formal definition of ds here. We're taking the variation of this function. And that's not hard to do because we treat the variation exactly like a differential everywhere except we're careful not to integrate against it. So what do we have? Well, we have 1/2 times 1 over the square root of this thing times the differential of what's inside. Now the variation times the variation of what's inside. So the variation of dxi dxi is just the variation of dxi times dxi plus dxi times the variation of dxi. Again, it's a product rule because, again, the variation behaves exactly like a differential except under the integral sign. But also, being linear as it is, it commutes with the regular derivative. So you swap these two around, and you realize that this is just equal to 2 times dxi summed into the differential of the variation. And this expression I went to pains to explain just a moment ago. So this is why this all looks so weird. You've got the differential of a variation, got a factor of 2 because you're treating the variation as though it's a regular derivative, and that shows up in the numerator of this thing. Now this thing here is just a definition of ds, right? So now you write, so the 2's cancel, this 2 cancels with this 2, and you write the differential of the path times the differential of the path variation over ds. And the way Landau and Lifshitz writes this is he writes this expression, dxi ds, as the 4 velocity, a component of the 4 velocity, multiplied by the differential of the variation. Remember, this is a function. It's the differential of the variation. So this part threw me for a loop for a while because this definition of the 4 velocity implies that he's defining the 4 velocity as each component of the 4 velocity as dxi ds, where ds is an integral along the path. And that means his 4 velocity is defined this way. The first component is gamma, and the second component is the vector, the normal velocity vector, times gamma over c. More typically in special relativity books, the 4 velocity is defined as not with respect to the differential along the space-time path, but with respect to the proper time, right? So there's a factor of c difference in all of this. And so this is normally the 4 velocity as we see it, and almost every modern textbook does this. So this is maybe an example of Landau and Lifshitz using an antiquated notation or a little idiosyncratic, or maybe I just don't have a lot of experience with a variety of different definitions of the 4 velocity. But certainly if you go to Wikipedia, you'll find the 4 velocity defined this way. And I didn't even see a note where they said sometimes it's defined that way. In fact, I'm going to go back right now and check. Right, so here you see it. The definition of the 4 velocity via Wikipedia, it doesn't even mention that there's an alternative definition that looks like dx ds, right? So whatever, I guess, it's just like I said, usually I don't think of Landau and Lifshitz as being archaic, But that is an interesting distinction. That is important for the flow of this. Otherwise, if you don't pick up on that, you're scratching your head. Isn't there a factor of C missing? And why are we defining U this way, right? Anyway, so now with that in mind, we start making all these substitutions. The first being, we're going to substitute for this. We're looking for the variation of the path. And that's really important to understand, right? The thing we're actually varying is the path, right? The action gets varied because we're varying the path. That's what this whole analysis was all about, right? It's ultimately a variation of the path. And when, even when we write down, we're going to vary the action, we really need to say, no, we're actually, instead of worrying about this variation going inside, we really need to worry about it coming outside, because we're varying this path, and we're varying S and we're varying xi, the path functions. So these differentials are what's changing. And so the point is, when we do this substitution, we substitute in for ds, we end up with this ui differential of the variation, right? That's where this function gets put in right here as a substitution for ds. So it flows ds, we get the mc, those are constants, it just drops right into there. And then, so that's the first variation, right? The second part is we need to vary this term, the term that involves the path and the field along the path. Now, what's important to understand is, again, we're varying the path. The field changes because the path is changing. In other words, we're on this path here, you have the field A mu x mu, right? But on the varied path, you have the field A mu x mu, where now x mu is orange, which stands for the varied path. That's a difference, right? So for some value of the path parameter, you're going to have two different values for the field. And this difference here is the variation of A mu, right? That's what we mean by the variation of A mu. It's driven by the fact that we varied the path, right? And we're going to reflect that in our calculation. So if we're going to now discover the variation of this term, right, meaning that we've taken our variation and we're moving it in here. We've already done this variation, right? That's what this stuff was. Oops. So now we're interested in the variation of this part, right? So with that in mind, we're going to use the product rule, right? This is a differential, and it treats it, except for the fact that you can't integrate in it, it works like a normal differential. The variation, this variation acts like a normal differential. So this piece here becomes the variation of the field times the differential of the path plus the field times the differential of the variation of the path. So now we have brought this term into this sort of, we've blown it up using the product rule. And so now we're going to clear these two differentials of the variation using integration by parts. We always use integration by parts. I love that thing. It just pops into this stuff all over the place. The calculus of variation uses it all the time. And when I do this, I think of, this is the language I use. The integral of u dv is uv minus the integral of v du, right? And of course, this is the antiderivative form of it, right? And if we call this the function u and the variation in the path is the function v, we have the integral of u dv equals u v minus the integral of v du, right? Likewise, we're going to do the same exercise over here, where now a plays the role of u, but the variation in the path still plays the role of v, and we get u v minus the integral of v du. So now you'll see that the variation has been pulled out by itself as a function, and we've traded it. We've traded the differential of the path variation with the differential of the field in this case, and in this case we traded the differential of the path variation for the differential of the velocity, the velocity. And so in those two cases, we're now going to have to start trading these. We have to trade out the variation of the field in favor of the variation of the path. Because remember, ultimately, the path is what we're directly varying. So the variation of the field, which we know is connected to the path, the variation of the field, I'm going to use this expression here. The variation of the field is the derivative of the field with respect to space times the variation in space of the path. Right? Mm-hmm. We make the variation of the field proportional to the variation of the path, and the only constant of proportionality that makes sense is the partial derivative of the field with respect to space, which is what this is. So everywhere I see variation of the field, I can replace it by this partial derivative summed into the variation of the path components. These are the variation of the field components, by the way. So this partial derivative, this sum is over j, and you're left with one index I. So that's an easy substitution to make. And then over here, now we have to make a substitution for the differential of the field, not the variation of the field, but the differential of the field. But that's really easy. It's sort of the same process. It's the partial derivative of the field with respect to space times the differential on the path, right? So this is the normal differential of the field along the actual path, right? And that's what this is. So this substitution is very easy to make. This substitution is very easy to make. And when you make all of these substitutions, you end up with this integral here, right? This piece of the substitution for the differential of the variation lands right here. This part's called the boundary part. It lands in a boundary term. Remember, we're integrating from the start to the finish, and this boundary term is going to go away because the variation is 0 at the boundary. So that term goes away. And then this part, the field variation, the variation of the field due to the variation in the path, which includes that substitution, that landed, where did that land? That landed right, I think that was here, right? Yeah, it's here, right? Summing over j. So that lands right here. And then this substitution, which required this integration by parts, and then this subsequent replacement of the field differential with the path differential, that landed right here, right? And then this part of the integration by parts that cleared the differential of the variation, that boundary part landed right here, but of course you have the variation again. It's linear in the variation, but the variation is 0 at the boundary. So that whole boundary term goes away, and all you're left with is this, which I am writing down as this expression right here. So that's the integral that we set to 0 based on our principle of least action. Okay, so now let's attack this guy. I guess the one part there was one step between here, and that is I'm now converting this differential with respect to the differential of the four velocity. I'm exchanging that for the differential along the path. So I get this differential of four velocity with respect to ds. And I'm going to do that everywhere. Everywhere I'm going to convert back to ds so I can pull a ds out of everything. And this is going to be a four acceleration. Okay, so the term we're going to work with is this expression. I just recopied it here, the variation of the action. And now I'm going to put everything in terms of ds. So I get this dxj, the differential of the path. Well, dxj is just dxj ds, right? That's not hard. And we know this from the Landau and Lifshitz definition is uj ds. So I can make the substitution here for dxj to be uj ds. And likewise, I can do the same thing right here. This dxi can become ui ds. So everything can now be in terms of ds. This expression over here is completely isolated from this, right? You're integrating this term. It's all linear in the sum, so you're integrating this term. So this term and this term are totally separate and isolated. And all the indices here sum to a scalar, right? I is summing, you're summing the i's with the i's and the j's with the j's. So the Einstein summation being in effect, I can swap these dummy indices as much as I want. So I can change the j to I and the I to j is the point. So this dxi actually becomes dxj, and then it becomes uj ds, just like this term. The reason that's important is it allows me to pull out a uj from this term and from this term, and the variation in the path, which is variation superscript I, variation superscript j, now they're both superscript I. So I can pull the variation out. And then everybody has a ds, so I can pull a ds out, and I'm left with this integral here. Where the variation, it's linear in the variation of the path, and it's being integrated over ds. So now I'm integrating over a real differential, a no-kidding differential, and I've got the variation out here. Phew. So now, using the principle of least action, I set this guy to 0. Right? So this whole thing has to be 0. And now it's the usual argument, right? The variation in the path is totally arbitrary. And being totally arbitrary, it can't be used to turn anything to 0 all the time. This must be 0 for any variation, right? Is the point. So I can't use that to turn anything into 0. So this integrand here, with excluding the factor of the variation in the path, that integrand must be 0. This looks like a force, right? So again, I'm going to write the force equals, and then this is what that force needs to be equal to. So I want to move that on the other side of the equality. If I did that, I would end up with a minus sign here. So to get rid of that minus sign, I flip these two around. So I get partial AJXI minus partial AIXJ, which it was reversed up here. So this expression must be true always in order for the variation to be 0. And that's sort of the end of it, right? Because now what I'm going to write is I'm just going to take this difference in these derivatives of the potential, and I'm just going to wrap them up into a single tensor. And that's what I'm going to call the electromagnetic field tensor. And this is a force is equal to the electromagnetic field tensor contracted into the velocity, the 4 velocity, right? The 4 velocity. And there's this proportionality factor, E over C. So it's still proportional to charge, and it's proportional to charge and linear in velocity, in 4 velocity. And this captures everything about the electromagnetic field. But it's sort of a notation thing, right? We've squeezed in this difference to be defined as this electromagnetic field. And so ultimately, this is our expression. And we can write it in its covariant form or its contravariant form. But this guy, combined with the fact that B is del cross A and E is defined as this expression of the 4 potential, is how we now must think about the electromagnetic field. From this point on, we're always going to think of it in terms of the electromagnetic field tensor or the 4 potential, but this is the definition that links the two together. And we can calculate this for each individual component, right? We'll learn the diagonal components are obviously all 0 because they result in the same derivatives being subtracted from each other for every diagonal term. So its diagonal terms are always 0. And whenever you see a tensor whose diagonal terms are always 0, you tend to think, there's a good chance it's anti-symmetric, right? But you have to check. So the 0, 1 term would be partial A1, partial X0 minus partial A0, partial X1, which is X0 is understood to be C dt, right? That's the time component. So it's C dt. So you pull out a 1 over C. And A0 is we've already defined the contravariant components to be the scalar potential and the vector potential. So the the covariant components is the scalar potential and minus the vector potential. So this term here becomes minus partial A, well, the first component of, well, let's see, how do I write that? The vector A's first component. Hold on. This is what it looks like, right? So the negative sign comes in from the fact that we're using the covariant expression for the 4 vector, or the 4 potential. And that ends up being the x component of the gradient of the opposite of the scalar part of the 4 potential minus 1 over c times the time derivative of the vector part, the x component of that, right? The x component of that. And of course, that's the definition of the x component of the electric field. And likewise, you can do the same calculation and get the y component and the z component of the electric field. You can realize that, it's anti-symmetric, is not hard to see. And then you can do the same calculation for a space-space component of the tensor. So you get an expression like partial A2, partial x1, minus partial x1, partial A2. And you realize that that's the z component of the curl of the spatial part of the 4 potential. And that is the definition of the magnetic field in the z direction. And again, you see antisymmetry. So that is how we end up with an expression for the electromagnetic field tensor. And you'll notice it's just sort of a notational simplification, right? In some sense, what you're kind of saying is the real thing, and I will put real in quotes, right? The real thing that matters, and it's very tempting to do this, right? The real thing that matters is that, oh, you've got this 4 potential. That's the thing that's really out there. And this is just shorthand for this, how the 4 potential varies in space. The problem, of course, is that, well, there's a lot of problems. First of all, the notion of real is philosophically loaded, and that's not really our job, is to peel apart the philosophy of science. But, the one thing we didn't talk about with the 4 potential is clearly this expression for the magnetic field, which is measurable. For example, there's some gauge uncertainty here, right? You can make a gauge transformation and come up with the same field. So you argue, I measure the field, so there's a 4 potential out there, but the 4 potential is only defined up to some gauge. So because of that, how can something be real if it's not unique, right? And that's what we're saying here, is A is not unique to give us what we measure as B when we do experiments. So maybe maybe A isn't so real after all. Maybe this is the real thing, and it's defined in this weird way. But how can a real thing be defined in terms of something that's not real? Well, that's a problem. So maybe you say, oh, no, we measure B and E. That's the measurement we make. So the measurement we make, that's definitive, so we can get the components of this guy. But of course, the components of this guy and the measurements you make depend on what frame of reference you're in. So again, you have issues of reality there. So there's a lot of these philosophical issues which are really fun. They don't worry us too much, right? We use these gauge freedoms and Lorentz invariance to our advantage in physics, right? We like the fact that that is the case. Well, and presumably there's some analysis where you can go the other way. I don't know what that analysis is, but I think there's probably an analysis out there where you land on this and you derive this. So there's I wouldn't be surprised if somebody could come up with one, or show me one. Maybe I've even seen one, but if I have, I've forgotten about it. Okay, so now we are totally settled on the fact that electromagnetism is no longer E, B, and E. It's now 4 potential and electromagnetic field tensor. That's how we think of it. That's our foundational ideas, and E and B are these curious things that are discovered in certain reference frames. And that's what will be the subject of our next lecture. Our next lecture, we're going to talk about the Lorentz transformation properties of the electromagnetic field tensor, and we're going to do a really cool example that I found in a very interesting paper That's not trivial at all, but it's actually quite exciting, and it fully exercises this. And then we shall move on to other topics.